I think what I'm going to do is I'm going to show you guys some demos. I've got a couple of live action ones, so sorry to you guys in Livingston if you can't make out the ones, but I've got a couple of tuning forks, and this is called a boom whacker. I use it with my daughter for music lessons, and I mean, basically you just use it and hit it, and it makes a sound. And so I'm going to talk with you guys a little bit about musical instruments and pitch today, and how that works, and we're going to talk a little bit about waves on like this kind of string that's going up and down. I think this app works a little better than when I just put the big slinky on the floor. Because when I try to swing the slinky on the floor, one, I get really tired, and two, it doesn't work all that well, mainly because of friction. And actually, that's a good way for me to start by describing this one right here, because this one works kind of the same way as when I would put that slinky on the floor. I mean, when I first start waving it up and down right here, yeah, it makes a pretty decent wave to start with, but I mean, by the end of it, there's kind of too much friction for it really to wiggle all that much anymore. Whereas on this one right here, I can turn down the dampening, and all of a sudden, yeah, now it's working way better. And so this is a principle that we've kind of already talked about here, where once the frequency starts to match, the amplitude keeps getting bigger and bigger and bigger. What did we call this in a previous section? What was the name? Resonance, yeah. Resonance is that same principle that causes that crystal glass to eventually break. Because if you can match its frequency with a different frequency, it keeps building and building and building until it gets, I mean, larger and larger and larger. And obviously this is getting crazy at this point here. So we'll just kind of restart to watch it again, right? But you can see that as the frequency matches, and it is somewhat matching here, the amplitude keeps getting larger and larger and larger. I can mess around with the amplitude. Start again here. Start with kind of a small amplitude. But I mean, it doesn't matter how small I start with the amplitude. As the frequency matches, it gets bigger, bigger. It'll get there. So, anyways, I want to show you a couple other little things that we can do with this thing here as a demo. One thing I'm going to do is I'm going to make it so that it's got a loose end right here. What it's going to do is it's going to put a little ring around a bar, and I'm just going to use a pulse. I just need to restart this. So I'm just going to shoot a pulse through this. See how that works? Roll on there, and then it's going to like reflect on the way back. And then this side right here, it actually reflects down at the bottom side. I'm going to restart this. I'm going to make the amplitude a little bit bigger. Today's goal is to talk about interference and superposition. And interference really can be thought of in two ways. You can have what's called constructive interference or destructive interference. And I imagine that you can probably intuitively figure out what that means just based on the words, right? Constructive interference means that if you were to say send one pulse and then another pulse, that was constructive interference. Right there, that's constructive. Right there, that was constructive. See how the pulses overlapped and they made themselves taller? What would destructive interference be? Right there. Or right there, that's destructive. Does that make sense? So the idea basically is that as a wave passes by another wave, if they add to each other in terms of amplitude, which is kind of that resonance concept, if the frequencies matches and the waves add to each other, that's a constructive interference. What does that do? Well, it makes something stronger. It makes it louder. Does that make sense? But if the waves happen to pass by each other kind of out of phase, not in sequence, like right here, for a brief second there, they're going to basically cancel each other out. See what I can do? Okay, so I'm just going to do it step by step. Step by step, all of a sudden right there, the waves have effectively, they cancel each other out. Does that make sense? Okay. You ever heard of something like a frequency jammer? It's not necessarily just a sci-fi sort of thing, right? That actually is a tool that would exist, right? Where if you can manage to match a frequency, only you're not matching it in a positive way, you're matching it in like an inverse sort of way, right? Where one wave is going like this, and the other wave has a similar frequency, only rather when this one is going up, this one's going down, you can actually cancel out a frequency, so you don't hear it anymore, right? What's the name of the company? Bose. Am I saying that right? Yeah. Right? One of their big groundbreaking things is their noise canceling technology, right? Well, what they try to do is they try to make it so that all other frequencies coming towards your headphones, it finds a way to basically remove them. Right? That sound doesn't just cease to exist. But at least in your frame of reference inside, your ears and your head, it manages to emit a similar frequency to whatever is on the outside of the headphones, so that you don't happen to hear it anymore. Does that make sense? So let me just play this one more time here. If I send a pulse like this, at least on the loose end, this is easier to see, right? If I send another one like that, that was deconstructive, and then that was constructive. So adds to each other, cancels each other. Adds to each other, cancels each other. Does that make sense? Now, I've only done this with just with a couple of pulses, right? You can imagine, though, if I were to add a couple other pulses into this, you get some pretty cool patterns going. Right? Where all over the place, you've got sometimes where it's constructive, and other times where it's destructive. If I just pause it all of a sudden, at this particular location right here, you more or less have destructive interference, where really there is no wave happening anymore. Right? Whereas down here in this section here, it was probably constructive because it seems to be adding to it, right? As I play a little more, that's not that one. Okay, here it's all kind of cancel each other out, but here it's actually gotten quite tall. Does that make sense? So that's kind of my first slide here. I want to talk about the idea of constructive and destructive interference. And hopefully it's fairly intuitive based on those words, right? You have two pulses going towards each other. Either they will overlap and become taller, like right here, or perhaps I've got a picture here where this one goes up and this one goes down, where they're kind of destructively interfere with each other, and it'll decrease them. So the word I want to use is called superposition. Superposition. Basically, it means that just add the height. If one of the amplitudes is supposed to be going up, the other amplitude is also going up, well, then just add them together. If one of the amplitudes was going up, but the other one's going down, well, then one's positive, one's negative, they'll cancel each other out. That's all. So that's superposition. The displacement of the combined pulses will be the sum of their individual ones. It's really wordy, but you guys get the concept? Either add or subtract, depending on which direction they're. So here's the slide I had to talk about the applet. I want to play with it a little bit more just because it's kind of fun. So let me start it again here. What happens if I put on the dampening? Well, what the dampening is going to do is it's going to make it so the pulse kind of encounters a little more friction. So if I were to throw a pulse through here like that, see how that kind of lame, right? Which is why I'm going to use the applet rather than real life. Because in real life, it probably would look more like this. I would shoot the pulse to the other side. By the time I got to the other side, it'd be about down, right? Which is what's happened when I use that spring in the past. So I like this because I can basically remove the friction. Another thing I can do is I can change the pulse width as well. What is a pulse width? What's that really a better name for, maybe? Your wavelength would work, or period. Either of those kind of work, right? If I change the pulse width to be really small, well, now it's a short little guy, right? Whereas if I make the pulse width really big, then you have a big distance between them. Does that make sense? As I pause this, from here to here, if we're talking wavelengths, is that a full wavelength? What is it in terms of how many wavelengths is it? Anyone want to take a stab at it? Is that a full wavelength? What proportion of it is it? Say it louder. It is half. Yeah, let me see if I can draw this. I'll have to do it with a pen because this isn't a whiteboard here. But essentially what we have here is, in terms of our graph, it's going down. We still need to go up and back down again though. Does that make sense? Because a full wavelength is from here to the spot where it repeats. And this is only it on its way back up again. It still has to keep going the rest of the way up and back down. So from here to here, we would call that half of a wavelength. Sorry that you guys can't see what I just drew on the board there. Hopefully you could hear what I said though. Basically from where the curve happens to be, that's half of a wavelength. Does that make sense? So that's one of the things I can mess with. What does a wavelength change? What if I have a higher or shorter wavelength? What does that affect? Maybe I should be more specific. What if it's sound we're talking about? What does that affect? The pitch, yeah. How high or low the sound happens to be, right? I'm going to use these more later, right? here's a couple of different pitches. One of them is lower, one is higher. Right? That's a pitch. And you can actually see, when I let you guys play with these in a bit, it actually lists the frequency on here. Right? So one of these is at 512 hertz, one of them is at 1024 hertz. Right? If you have 1024 hertz, it means you're cycling way more times in a second. So it means you have a very short, compressed wavelength. Does that make sense? If you have a high frequency, you're going to have a short, compressed wavelength, because you have a lot of cycles happening in a second. If you had a frequency of 1, it's going to take a sweet time getting back and forth, right? If you have a frequency of 17 times. Does that make sense? Well, this guy right here is 512. That means a wavelength is going up and down 512 times in a second. That's actually a lie. Why is that not exactly true? Why is that not how sound works? Does sound go like this? It pulsates. Remember the difference between longitudinal and, what was the other one? Transversal, I think it was? Waves from yesterday. So you can still use the same principles, but basically it pulsates out instead, as opposed to up and down. And it's got the same principles. So that's what a frequency or a wavelength will do. The other thing I can mess around with here, though, is not just the pulse width, but I can also mess around with the amplitude. Oh, before I get to that, what if it's not a sound wave? What happens if you change the frequency of like an electromagnetic wave? Then what does that change? Say it louder. That's a good way of putting it, yeah. What if it's a very high frequency? Do you guys know what some of the high frequency waves are? What was that? Gamma. Yeah, gamma is the most high frequency of all the radiation. You're talking gamma, X-rays. Those are sort of waves that are so short in terms of their wavelength, right? The distance between, as they go up and down, that they can actually penetrate through material. Right? Whereas the longer wavelengths, the smaller frequencies, the ones that don't happen as quickly, those are things like your radio waves, your microwaves. Does that make sense? And those, I mean, anybody have poor reception in this building sometimes? Right? One of the reasons why is that those waves are literally getting blocked by the concrete right here, because the waves cannot reach your cell phone. Right? Whereas, X-rays and gamma rays, they can go right through. There's actually some theories about smaller waves than even gamma rays called cosmic rays, which are supposed to be even smaller than that. I don't even know much about those, but that's the theory. Okay, let's talk a bit about then what happens if I change the amplitude. If I were to play with this thing and make the amplitude be bigger, I shoot a pulse through it. What does that affect? Is that louder? Yeah, energy is the best way of putting it. If it's sound, it makes it louder. Yeah. If I do this, or I do that, have I changed the frequency? Well, either way, you should have heard the same pitch. Maybe you didn't hear the first one because it wasn't very loud, right? But all you've done is you've made it louder. You've added more energy to it. Right? Same sort of concept with any sort of other waves. You've just made them taller waves. If you think of it like a wave in like a water system, and you are a surfer, this means there's a bigger wave to ride. That's all. And so if you happen to be somehow going up and down over top of those waves yourself, on your surfboard or something, this means you have more energy. That's all. That make sense? I want to show you something kind of cool here, if I can pull this off. I was playing around with it last night, so hopefully I can make this work. Take down the amplitude. That's pretty good. I'm going to try to oscillate this thing here. No, it's not what I'm looking for. Oh, hang on. It's close. Okay, 2 seconds. Bear with me. I'm going to try to create what's called a standing wave if I can pull it off. I should memorize what the settings were from last night. No doubt. There we go. Okay, this is almost what's called a standing wave. It's not perfect. That was better a second ago. I don't know why it stopped there. A standing wave, if I can kind of pause it, what ends up happening is that basically, if you see it, it's almost like it goes up, down, and there's a few points that never move. Like right here, this point right here ideally would never move. And this point right here would really never move. And this point would never move as well. And what would just happen is like the top of this would just completely go straight down there. Does that make sense? And this bottom minimum, it would go straight up here. And what you end up getting are called your, remember the term nodes? The nodes are kind of like the middle points. Like this one, and this one, and that one, and that one. They really never move if you can make a standing wave. And it basically just goes straight up and down, and up and down, and up and down. Does that make sense? Now, this one's not perfect because you can see how it kind of messes up for a little while there. But we should get a standing wave back in a second here. Where for a bit there, see how it's just going literally straight up and down like that? Right? And then now it's kind of like going side to side and kind of wriggling like a snake again. Let's see. Right about now, we have about there, that's a standing wave. Where it's kind of really not moving. You know what I mean? Like when it's kind of moving side to side. It doesn't move side to side. That's called a standing wave. So, maybe I'll play around with that more later. Let's talk about the rest of our notes though. So, we gotta watch this video. This is a cool video.
1, 2, 3.
So this is someone who in their, I don't know, backyard somewhere, they hooked up a whole bunch of bowling balls, a pendulum, on some sort of big system here. And what ends up happening here is they all have a different string length. How like we use the formula period equals 2 pi for L over G. Remember that formula? Really, the only thing that affects the pendulum's period then is gravity and the string length. And so what they've done here is they've varied all of the string lengths. So at first when they started out, really nothing, you know, they just kind of waved back and forth, really cool, right? At this point here, they're just kind of all going haphazardly. But this is one of the cool things about physics in general, is that if you wait long enough, what seems to be chaotic and have absolutely no pattern will all of a sudden just match up. So you just gotta wait. See that little pattern there, where almost like a whole line just kind of went back and forth? There's more cool patterns if you watch them. Again, it kind of looks random and haphazard. There's really no order to the system. The official scientific name for this.
Whoa!
Look
at that.
So now you're back to what appears to be haphazard again, right? There doesn't seem to be any order to it. The word for that in chemistry, and in science in general, is called entropy, which makes it seem like it's really just random, right? But the universe doesn't seem to really work that way. It seems to be at random at first, and then all of a sudden, things just seem to line up again. Eventually, we'll actually have this thing go in one big line again. It just needs to take wait long enough.
How are they doing that? It's because some of the strings are longer than the other strings. So the ones with the longer strings go more slowly than the ones with the shorter strings.
The instructor in the background is kind of explaining that there's different lengths of strings, right? Like this one that's in the foreground probably has a very long string, which is why it's taking a long time for it to come all the way back and forth. Whereas some of the ones in the far background, there's a wave again now. See how it kind of has that wave pattern again all of a sudden? It's not perfect, it's friction slowed it down. See the wave showing up again now? Each one of those strings is a different length, and then all of a sudden, a minute and a half later, they're all back to more or less being the same length. Isn't that cool?
What's up again?
So, kind of a good demonstration of how, you know, a lot of things just kind of fit together, including a wave, right? Like right now, you can actually see to some degree the wave kind of going up and down, and it doesn't. Oh, just take that back off. Just escape here. You can see as it was going back and forth, right? Some of them took a really long time as a pendulum to go back and forth, right? Whereas other ones were a lot shorter. Right? And when everything just matched and the frequency and the periods lined up, Sometimes they all went in a big line, right? Sometimes they kind of had a little bit of an S curve to it. There was that section in the middle where like one row was going this way, one row was going this way. So I like that video because I think it just kind of shows how physics is, well, sometimes it seems just completely random. Like there is nothing, there's no order to anything. That's the word entropy. It's not on any test, by the way. It's just a word you might hear. Where it just seems like there's no overlying principle making anything line up. And then all of a sudden, it just lines up perfectly. That looks really cool. So, anyways, I like that video. I thought that was a cool one to show. Alright, back to our notes. What else do I got here? Alright, so I guess more just on the same concept here of as these waves kind of overlap each other, right? If you've got wave 1 and wave 2 and they hit each other, all you need to know is that here they're going to make a taller amplitude. But another thought though, they're going to phase through each other. They don't just stop, right? This pulse that went left and this one that went right, they'll keep doing that. Right? They will look like they did before they started. Okay. This is what I was trying to show you, that standing wave. The idea where it can get reflected off of the other side and then bounce back up and down again. I know why it wasn't working well. I need to change this to fixed end. That's why. There we go. That's close. I just need to change the frequency a little bit. Reset. Too much frequency. Just too much. It's not bad. It's close to a standing wave. It's not perfect, but do you guys see how there's a point right about here that doesn't really seem to be moving all that much? Ideally, this ball that I'm pointing out here wouldn't move at all. Does that make sense? And then like this green one in the middle here, it does a fairly decent job of staying more or less still. Same thing with this one right about here. It's not great, right? And all that really happens is this goes down, up, and it creates what's called a standing wave. You guys get the concept here? Right. So this, I'll turn this off now. This diagram can hopefully kind of describe the concept where what you have is in increments of 1/2 wavelengths. You have this little section, it'll go up, and then it'll go down. And then when this section is down, this one will go up. And they all happen in increments of 1/2 a wavelength. Each one of these in-between nodes is 1/2 apart. This is actually really important though, because this gets to the next part of my lesson. This is how we make musical sounds actually, is when we have wavelengths that are resonating at certain frequencies that fit inside instruments. Like for example, you guys know how a trombone works, where like the trombone, they blow in and they have to move like the little, that part there, right? And as they change the length of the instrument, it means that fewer or more wavelengths fit inside, and therefore that changes the pitch. Or a trumpet really works the same way. A trumpet's a really complicated instrument. There's 3 buttons on the trumpet, and they all open and close different valves. And so as the air loops through all of those little twists and turns in the trumpet, it either lengthens the length of the tubing, or it shortens the length of the tubing, thereby allowing you to have either more or less wavelengths. And by having more wavelengths, let's say this properly. If you shorten the wavelength, you would increase the frequency, making it a higher note. If you lengthen it out, it should then make it a lower note. I hope I did that right. Because it would have a larger wavelength. So let's talk about that next. I brought a kind of a couple of demos to talk about here. So you have 2 possibilities here. You can have instruments that are either a closed column or an open column. Okay. So like for example, this boom whacker here, it's an open column because you can see right through it. Hello. My daughter's love playing with these things, right? And as you hit it, you guys can hear there's a pitch to it. Out of curiosity, how many of you guys are musically inclined and have taken some music lessons? No, you have. And like know a little bit about music? Like you guys know how there's different notes on the scale, like C, D, E, F, G, A, B, and then it loops back around to C again. You guys have heard that before? Okay. So what I've pulled out here are some of the different pitches that are all the note C. And so one of these is a low C. So this should be an octave above it. This should be an octave above that. And then this should also be a C. I don't know if you guys can hear the pitch there. So I'll play it at the same time. But these should be the same. These should be both a C. They're just octaves above each other. I don't know that you guys can hear that. Like I know I'm pretty used to it. So those will actually sound the same. I'll let you guys play with those later if you want. Okay. Here's the physics behind how the music works then. If you have a closed column like this, it means that you need a quarter of a wavelength inside. See if this picture makes sense. What has to happen is the wavelength has to basically be a standing wave where this will like reflect over to here and back and forth and back and forth. Does that make sense? Like this will reflect to here and back, and this will reflect to here and back. But this point right here, that'll be the node in the middle, the point that never moved. Does that make sense? Like when I was showing you this diagram back here, how there's a point that never moves. The node has to hit the closed side right here. And basically from here to here, that's a quarter of a wavelength. Because it would still have to come all the way back down to start, then it would have to go down to the bottom, and then it would have to come back again. So this distance right here, quarter of a wavelength. That's the math behind how a closed instrument works. I'm thinking like a drum might fit that, where there's like a backing to it. So here's the same thing. Here's a closed column. You guys kind of visualize how this works? This is your node. It would have a standing wave bounce up and then bounce down, and bounce up and bounce down, and bounce up and bounce down. And the wavelength of that particular size there is 1/4. From here to here is a quarter, back to there is a quarter, up to there is a quarter. So this is 1, 2, 3, 4. You need a quarter of a wavelength. If you can find a wavelength, remember the formula from yesterday? That the velocity is the wavelength times your frequency. We can then find the frequency and tell you what pitch that note is going to be based on the wavelength that fits inside there. By the way, it's actually possible to have more than one type of wavelength fit inside. You could actually have like a portion of another wavelength sitting inside, and that's how like you have your octaves. If that makes sense in the music terms. That's how you can have a C, but then you can have a C that's like the C above middle C and the one above that. So that's how you can actually have different like overtones to it. Here's the one I want to test today. This is an open column. So this is the boom whacker we have here. Okay. Ideally, the math behind this is that right in the middle is where we're going to have a node. There's going to be a node right in the middle here. And you have to have an open wavelength of your standing wave on both sides. The math then for this is that you need to fit half of a wavelength inside this tube. You guys visualize that? From here up till there, that is half of what normally a wavelength would be. Normally a wavelength would go all the way from here up to the top and then back down again to the bottom. That would be a full wavelength. So from here to here is half of that. Does that make sense? So all you need to do then to figure out the pitch of your instrument is you need to measure this. So I'm going to try this one after I do our first example. I'm going to see whether this actually has the same pitch, hopefully, as what these guys right here said they should. And then you guys can play with them later if you want. So here's our example. Let's say that you go to like one of those old-fashioned churches that has like a big organ. You know, like good Christmas hymn kind of organ, right? It's got like those big columns, right? And you measure the column, it's 3.6 meters. Based purely on that, we should be able to tell you the frequency of the note it will play. Just based on the size. Just like in a second, I'm going to measure this thing here and see if I can find its pitch. So, if you can kind of picture this example here, you've got a big cylinder, and the open-ended cylinder, it is 3.6 meters. Really big organ, right? 3.6 meters is like taller than this roof, probably. Probably the size of the roof. That makes sense so far? In order for the organ to make sound as an open-ended thing then, here's how the wave will look. You'll have a node in the middle, and you would have a wave that would look something like this. This is where it would go, and it would bounce up and down, so this point here would never move, and it would look something like this. Where from here to here, this would be half of a wavelength. So far, so good? You need to fit half of a wavelength inside your open tube. Well, if half of a wavelength is 3.6 meters, then what is a straight up full-on wavelength going to be? Times it by 2, 7.2 meters. So far, so good? So we now know what the wavelength of our sound is going to be. We know the distance from here to here was 3.6. That's half a wavelength. We doubled it. So that's our first part. But we also know the velocity. Because we learned yesterday, if you don't get told this information, the speed of sound is about 330 meters per second. Can we figure out what pitch this organ will be at least this particular tube will be at? Well, the pitch is the frequency. So we need to use yesterday's universal wave equation. This is the only math we do today, by the way. Your velocity is equal to your frequency times your wavelength. So 330 equals your frequency times by 7.2. So divide by 7.2. Someone help me out here. What's our frequency? 45.83. Say it again. 45.83. So let's call it 40. I guess just 46 then. What's the unit for that? Hertz. Yeah. Okay, a little bit of perspective. For any of you guys who are musically inclined, I'm teaching my daughter piano, by the way. Kinsey's 4, and we're doing piano lessons. If you know how like a piano works, just draw the rough piano. And if not, you're getting a brief music lesson today. So this is kind of like a rough keyboard. How many of you are kind of familiar with how like a keyboard would work? You know your notes, right? Like this is C, D, E, F, G, A, B, C, D, E. That would be F if you keep going. Right? So I have a couple of the tuning forks here, and when someone goes to tune a piano, they probably are using these to recognize whether or not they need to like tighten the string or loosen the string. So as I look at this C is listed to be at 512 hertz. And I believe this is middle C, I think. Might be one above middle C. The next one that I have here, oh, I should have done this in a different order here. We'll make this one 512 hertz. This one right here is actually at 256 hertz. And then the last one I have, the really short one, if I were to continue the piano way further up, is at 1024 hertz. Can you guys see the relationship in those numbers? Yeah. Why is it doubled? Well, because you either have more wavelengths, twice as many wavelengths, shoved into whatever instrument you have, or you have half as many wavelengths. Does that make sense? So, for a little bit of perspective, by the way, if you had 46 hertz, is that a low or a high note? Take a guess? That'd be a really low note. Yeah, right. As you listen to these, here I'll play them for you. You can hear the difference. This is the 256. As we change the frequency, it should be going higher. So that should be a very, very low kind of note there. So I want to do a quick test here then. This is what I use with my daughter when we play musical instruments. She gets to play the boom whacker. You can see that pitch there. It's not perfect, right? But it's actually off by an octave or two. I want to measure this thing, and I want to calculate its frequency. Okay, so we just need a measuring tool. What does the diameter affect? Hey guys, do we want breakfast?
Hey, so can I just talk to your kids first?
Go for it.
Okay. So there's some changes to the program, and it comes from the people who provide us money for the program, okay? So there's two things to know. You can only take one of each food group. You guys are smart enough to know what that figures. but that means, right? Because sometimes you have G strings added over, you can only take one or the other. The second one is when breakfast is done, it's done for the morning, okay? You can't come in an hour and say, geez, now I'm hungry, can I get food? You need to eat during this block, okay? And we're just seeing a lot of food waste, so you just be respectful. And if you're not hungry, don't take stuff. It's probably more the little kids because you see it more down in the little kids area, but might as well tell people, everyone has the same message. Okay, come on, that's it. That's all I got.
Thanks, Brian.
And muffins should actually be coming sometime the next day or two. And they will be.
No cheese.
There's 4 cheese strings.
More cheese.
3,
You want one, bro?
2, okay, 1.
I don't want
Oh
one.
my God, I can catch it. I want that.
You want an orange? Anybody? Breakfast?
Thanks, guys. Okay, so let's go back to my boom tube here. We're going to try the same calculations for this because that was my last slide, right?
Yeah.
Okay, cool. So the tube here, I'm just measuring it real quickly. First question, though, I didn't quite get to. How is the diameter going to change things? What does that affect in terms of our wave? Amplitude, yeah. Right? So as the diameter is changed, it affects how loud the thing might work. So I don't need to measure the amplitude, but I do need to measure the distance of this tube here. And so I have a strong feeling it should have been 30 centimeters, but it may be slightly out. I'm going to go with what I officially measured it as. I've got 31 millimeters. Sorry, no, that's not right. That'd be 30.1 centimeters. Yeah, let's go with 30.1 centimeters. But it's just slightly over the 30 mark. So let's redo the exact same calculation. If I measure the tube to have a distance of 30.1 centimeters, that would be what, 0.301 meters? So far so good. That would then be equal to 1/2 of a wavelength based on how this works. So all you guys need to memorize is that it's half of a wavelength in an open-ended tube and 1/4 of a wavelength in a closed tube. So we need to double that. So 0.602 meters is our wavelength. Our velocity is the speed of sound. I actually haven't tried this before class, so I'm really curious to see how this will work out. Let's find our frequency. Velocity is equal to frequency times wavelength. 330 is going to equal your frequency times 0.602. So divide by 0.602. What did you guys get? What's it? 548? Okay, so I'm just going to grab the tuning forks I have here. This one right here is at 512 hertz. So hopefully that's the one that's supposed to be fairly close. You guys can mess around with these later, but ideally these should hopefully have about the same pitch then. Yeah, give it a try. See whether you feel like these two have the same pitch. Anyways, that's the end of my lesson. You guys can mess around with the tuning forks and the boom markers if you want. Just hit the one, put it up to your ear. By the way, if you hit these things too hard, there's actually, I don't know if you guys can hear, there's an overtone. This is a lower note. If I put it up to my ear, I actually hear the octave one above it there. So sometimes when you hit it hard enough, you actually get both like a low frequency and a high one at the same time. So hit it and then put it up to your ear to hear it, because this actually has a low frequency. It sounds really high, but try these ones as well later. This one's more like a even though it sounds way higher. Physics and music